Hi, and welcome to Stone Rose 35's YouTube channel. What I want to show in this video is a comparison, first a theoretical one between these two platforms, and then also with some audio, some semi-theoretical audio samples, where I mainly compare floating point processing in audio with integer processing for the exact same algorithms, which is, I think, quite a unique thing to do. And in the second part, I'm gonna play through. I actually have two versions of this board, one with a Daisy Seed and one with a Raspberry Pi Pico with the audio board. And I'm gonna play through guitar, and of course the electronics are quite different, so you're gonna hear sound changes, but they may probably not due to different algorithms, but rather to different audio codecs and so on. So let's start. I've just made a little comparison of these two boards. The Raspberry Pi Pico is a general purpose microprocessor board. It features a dual core ARM Cortex M0 Plus. It's going to be a bit geeky in this section. Um, Most important thing to note is it doesn't have a floating point unit, and it's one of the more basic ARM Cortex processors. On the other hand, we have an Electrosmith Daisy Seed board, and this board is specifically designed for audio processing. It has, for example, has a built-in codec and extra RAM and so on. It's based on a single core Cortex M7 processor with a floating point unit, which is important, and but it's single core as opposed to the Raspberry Pi Pico, which is dual core. The Raspberry Pi Pico works at 120 MHz, of course up to 132 MHz would be possible without overclocking, while the Electrosmith Daisy Seed works at 480 MHz. So if you roughly, since it's dual core, you can roughly calculate 120 by 1.8, so you just, though I expect it to be less than half as fast as the Electrosmith Daisy Seed board. Regarding memory, the Raspberry Pi Pico has, or the board itself has 2 megabytes of external flash and 264 kilobytes of SRAM, which can be used for delay buffers, among other things which are needed by the software. While the Electrosmith Daisy Seed has more complicated memory sections, it has 1.128 kilobytes of internal flash, then 8 megabytes of external flash, which requires to write extra codes to access it in a meaningful way, and also to upload firmware to this external flash, which is quite a task to do. It has 412 kilobytes of internal SRAM and 64 megabyte external SDRAM, which is huge for a simple microprocessor board like this. I think the Electrosmith Daisy Seed is the only board which I know which has this kind of shape with that much amount of memory or RAM on it. Regarding audio processing, it's pretty similar. I've implemented it that way that it supports 48 kHz sampling rate, and the Raspberry Pi Pico board has a 16-bit resolution, while for Electrosmith Daisy Seed we can use the entire 24-bit resolution from the codec. And just a little side note, the audio codec built in the codec board, it also has a 24-bit codec, but of course we have to downscale it to 16-bit because the entire processing cannot be more than 16-bit without sacrificing lots of performance. And regarding the number crunching aspect, the Raspberry Pi Pico, as mentioned before, uses integer processing, while the Electrosmith Daisy Seed uses floating point processing. So what is the difference? This is a slightly academic slide. I tried to be as simple as possible. Integer arithmetics, of course, were 16-bit. That means we have 64,000 something equally spaced values, which are then mapped from -1 until almost 1. And one important fact here regarding audio or general signal processing is that values exceeding this range cannot exist, and clipping can happen at every additional subtraction, basically. And regarding the data path, we have a simple but lossy transformation at the analog to digital converter from 24-bit to 16-bit, and at the digital to analog converter from 16-bit to 24-bit. As opposed to floated arithmetic, we encode a floating point number as something like a mantissa times 2 to the power of an exponent. And that means we have around 0, the values which can be represented are more densely spaced than the values further out, which suits us since we renormalize our audio values in a range from -1 to 1, and the more the bigger they get, the more the coarser the resolution gets, so to say. Important to notice here is that the audio signal is artificially limited to -1 to 1, and clipping actually can happen almost only at the transformation from the digital to analog converge only. Because in the end, the data sent to the codec is again an integer number. Of course, we have to make integer to float transformations. Regarding the implementation of all these algorithms, where are the biggest differences? Is actually every time when we have to process, like for example, for dynamic compression, we just have to look up volumes, and for integer or like for distortion, wave shaping with integer processor, I actually every value that could exist among the 65,000 has a specific output value, so we can implement a simple lookup scheme, which is really fast and just without much computation maps each input value to an output one, as opposed to for floating point precision, we cannot do this anymore. We just have to apply interpolation scheme or actually functional approximation, which is obviously there's going to be some numerical differences which might be hearable. Of course, there are many differences between the Electrosmith Daisy Seed and the Raspberry Pi Pico in terms of hardware layout, in terms of programming, but I won't go into detail here. So let's start with the theoretical sound comparison. I'll start with YAMP simulation. By the way, on the left side, this is a screenshot of a little test application I made. This is a little Python app which allows me to test algorithms and how they sound without actually always deploying them to a real hardware. And I've did this for, of course, for the Raspberry Pi Pico and for integer processing also, and also for float processing. And for this comparison, this comes in quite handy because I can set the exact same parameters and then run it through both programs. So let's start with the AMP simulation with some settings. I don't explain this in detail because you can see it, and when we listen to it and how it would sound on the Raspberry Pi Pico, it's like this. The exact same sample with float processing sounds like this. Actually, I've been listening to this quite a bit. I hear some slight differences, but maybe this doesn't come through over YouTube. By the way, we'll also put the sound sample on a homepage I newly have, and I also put the link in the description of this video once it's available. Let's move on to the compressor. For a sound sample, I used a drum loop I found somewhere on the internet, and with not the heaviest compression, but as a ratio of 1:4 as a threshold of about -45 dB, you should be able to hear the compressing effect on the drum sample. Let's start again with integer processing. And floating point processing. I barely can hear a difference. It's really difficult to say, but maybe you can. I don't know. Just and then of course I don't compare every effect because otherwise this video would be 1 hour or even more. It would be really boring. many effects like chorus where there you can't hear any difference at all, which is really the same. Everything which is modulation based, also a delay, of course, a simple delay sounds exactly the same, I would say, on a floating point processing and with integer processing. The last, where probably the biggest differences are hearable, maybe mainly due to the how clipping works, is with a reverberated sound. Is again as a sound sample, I again use the drums of from before. And floating point processing. At least to my ears, the floating point processing sounds quite a bit like cleaner, more because with integer processing, the sample is quite has quite a high level sometimes. So probably within the reverb algorithm, some clipping already occurs. While for floating processing, this probably, if any, it's clipping occurs only at the very end, and this makes a difference in the sound. Let's move on to the practical comparison. I decided to do this using harmonica and not guitar. I'm more familiar with playing harmonica than guitar right now, and also it allows me to more easily change sounds and change settings when I have one hand which is free. Let me quickly explain the setup. On the left side you see it's not the Pi Pico device anymore, but the digital audio processing device, which has the Daisy Seed board of Electrosmith included. And on the right side you see the Raspberry Pi Pico as a multi-effects device. Of course the hardware is very much different. This one has symmetrical outs, microphone input, and so on, while this one is the more basic version. On the front you see a splitter. When the red light is on, that means the signal is routed to the Raspberry Pi Pico, and if the green light is on, the signal is routed to the Electrosmith Daisy based effects board. The three knobs are the same for both devices. Of course, I'm not going to use the foot switches, I just use the same user interface as this here. Probably you can't see it on the video, but one interesting thing is also just to pay attention to this third bar seen on the screen, which shows the CPU load on both devices. Theoretically, this should be a little bit lower on the Electrosmith Daisy board. We will see how it performs. So let's start with the first setting, which is the amp simulator. I tried to put the three knobs the same amount. So this first one is high cut, I put it in the middle. Gain is also centered, and the effect amount, in this case delay amount, is at what is this, 9 o'clock setting, I think. Try to play the same thing. Sounds a bit different, but maybe this is also due to some slight volume differences. Let's add some more bass, for both settings like this. One thing to note is also like how I cut the mic also affects the sound. I wasn't really aware when I decided on doing this using harmonica. But anyways, let's move on to another setting. I think I skip. The equalizer is going to sound the same, but I'm playing through this acoustic processor.
It's quite suitable for harmonic as well. Maybe we just have to change the settings a little bit. But what is clearly noticeable, at least to my ears, is that already the clipping which occurs within the reverb part of this setting. So let's move on to another one. Some reverb setting maybe. Let's turn up decay. And the third parameter is not used, so we can put it to 0. Then start with the Daisy C once again. I heard some differences, but maybe it's just a programming mistake, like feedback value being not the exact same on both devices. Let's move on to a third, and then I think we just end this practical comparison. So I made a comparison using the pitch shifter effect. I'm shifting down by an octave, and this is one of the effects where I really don't hear any difference, because it's actually pitch shifter is a rather simple delay-based effect which uses 3 delay loops, and of course in theory clipping could happen earlier with integer processing than float processing, but this doesn't affect the sound in any ways, I think. But let's hear a sound sample. So what are the next steps regarding these little devices? Of course, implementing the exact same algorithms on the Electrosmith Daisy Board was for me an interesting and nice exercise to do. But of course, with the Electrosmith Daisy Board, many different things could be done. And also all the extensions I made for the Raspberry Pi Pico, they actually, lots of this code which handles the foot switches and the interface actually should work or works on both devices. And this now allows me sort of to go in 2 directions, one with the Raspberry Pi Pico and with the Electrosmith Daisy Board. So I planned, or what I've already done, I've designed a PCB which accepts both the Raspberry Pi Pico and the Electrosmith Daisy Board, as where you can sort of connect both the Raspberry Pi Pico and the Electrosmith Daisy Board. So the same extension is going to work with both boards, of course, adding the correct software. There's another implementation steps I have to do for the Electrosmith Daisy Board. The Raspberry Pi Pico supports firmware upgrade via USB, and for the Electrosmith Daisy Board I just have to add this feature to make it really usable as an end user, so to say.